Okay, everyone, welcome back. Thanks for showing up again today for the live stream. We have a few minutes. Would anybody like to ask me any questions? Good morning. If you have two midterms at the same time, see one of the instructors involved and ask them if it's possible to shift the timing a bit or to find some other accommodation. The 2402 lecture today is at noon, so that I can have 20 minutes or so to eat my lunch between lectures. So for those of you who happen to be also in my 2402 class, I sent a note about this and also posted on the CU Learn forum. Hydro Ottawa is going to be cutting the power to my house today at 2 o'clock in the afternoon, between 2 and 4, which is exactly when our lecture would normally be. So I'm going to run that lecture at noon today. If you miss it, that's okay. The recording will still be available on YouTube forever. Yes, so after today's lecture and maybe a little bit more in the following lecture, you'll be ready to tackle anything on assignment 2. So after today's lecture, you'll be able to tackle anything. Maybe we'll see a few more examples in a subsequent class. Okay, so as you can see from the board here, today's lecture is about recursive functions and more generally about things like recursively defined sets. And in terms of functions, here's an example of one such function. So it's a function from natural numbers onto natural numbers. So those are the non-negative integers. And it's recursive, meaning that the definition of the function actually involves the function itself. So this is quite a simple one. It has two cases. So just like when you're doing programming, recursive functions need some base cases. They can't always just call themselves. So in this case, the base case, so this is a function that takes an argument n, and when n is equal to 0, the value of the function is 3. Otherwise, if n is bigger than or equal to 1, then the value of the function f of n is 2 times f of n minus 1, so it calls itself with the argument n minus 1, multiplies that by 2, and adds 3. So that's the definition of the function. And now you see that for any non-negative integer n, I I can figure out what the value of this thing is, right? So for example, what is f of 1? Well, according to this definition, it's in the second case. So it should be 2 times, well, n minus 1 when n is 1, that's 0, plus 3. And what's f of 0? Well, f of 0, we already have it here. It's directly defined as 3. So this is 2 times 3 plus 3 is 9. Okay? So we can write that down here. So here's n is 1. F of n is 2 times 3 plus 3 is 9. Let's try f of 2. Well, f of 2 is 2 times f of 1. Plus 3. And what's that? Well, f of 1 is 9. So this is 2 times 9 plus 3. That's 18, which is 21. So we can write that down. And we can keep going this way. F of 3 is 2 times f of 2 plus 3. That's 2 times 21 plus 3 is 45. We get a 45 here. And we can keep going. F of 4 is 2 times f of 3 plus 3. That's 2 times 45 plus 3. That's a 93. And so on. So we could do this forever. What this shows is that for any non-negative integer n, this function is well defined. We can compute its value. So there it is. So it's perfectly useful that way and well defined. But what it's not particularly useful for is for us really understanding, getting a feeling for this function. So it's defined recursively, and for us that's hard to imagine what this thing looks like. We can write down lots of values to get an idea of what it looks like. We might make some guess that, well, it's kind of growing like powers of 2, because each time you compute it, so when I want f of n, I start with f of n minus 1, and I multiply by 2, so that makes it twice as big. And then I add 3, so that has some other effect, so it's not just powers of 2. So we'd like to really understand this thing. And so let's make a wild guess. And we'll guess that f of n is equal to 3 times 2 to the n plus 1 minus 3. Okay. So maybe we have really good intuition, and after looking at these first 4 values, we saw immediately that it's following this pattern. And, well, so we guess this. And we can check for those first, actually 5 values of the function, that those things satisfy this equation, that this is true. But just checking it for 4 or 5 values doesn't really prove anything. What we would like to do is prove it formally. Just before we do that, there's a question here that asks if I will be going over the proof of the infinity of primes. I don't think I'm going to bother. If you want to see it, you can look at the other lecture video. It doesn't have any direct relevance to any of the assignments. So we did the Erdős-Szekaros theorem instead. Okay, so we have this claim and we would like to prove it. So these recursive functions really naturally lend themselves to proofs by induction, because especially ones that look as simple as this, because really, you know, the value of f of n, the thing we're trying to understand, is defined in terms of f of, in this case, n minus 1, but in terms of a smaller argument. So it seems really natural to use induction here. So let's prove this by induction. So, and by induction on the value of n. And actually, let's give ourselves lots of space here. So when we do an inductive proof, first thing we need to have are one or more base cases. So this is the case here, n equals 0. And usually from these functions defined this way, the base cases are kind of obvious, because the function is defined in some way that says, well, it's 3 if n equals 0. Maybe if it's more complicated, it might tell you the value when n equals 1 and the value when n equals maybe even 2. And then there's the general term. In this case, it's quite simple. There's one special case when n equals 0, and then there's the general term. So the base case ends up being this special case. And we need to verify that this formula is correct in this case. So let's write this formula down for n equals 0. So the formula says that it's 3 times 2 to the 0 plus 1 minus 3. That is equal to 2 to the 1 is 2. So this is 6 minus 3 is equal to 3. And indeed, 3 is the value of f of 0. So the base case checks out. So we've established that this theorem is true, or this claim is true, at least for n equals 0. So now we want to do the inductive step. So for that, we're going to assume that f of k is equal to 3 times 2 to the k plus 1 minus 3 for all k starting from 0 and counting all the way up to n minus 1. So this thing here is called the inductive hypothesis. And now, assuming that this inductive hypothesis is true, which is almost what we need to prove, except we need to prove it for f of n, and this inductive hypothesis only assumes it's been established up to n minus 1, we're going to have to try and prove it for f of n. Okay. So now we want to prove for f of n. And it almost, all these proofs almost always go the same way. So f of n, the definition for n bigger than or equal to 1 tells us that it's 2 times f of n minus 1 plus 3. That's just the definition. No leap there. Now, we have this inductive hypothesis that says, well, we actually know the value of f of k as long as k is between 0 and n minus 1. In particular, we know the value of f of n minus 1. It's given by this formula here when you take k equal to to n minus 1. So the inductive hypothesis says that this thing here, we can blow it up into using this formula. So it's 3 times 2. Now, applying this formula with k equals n minus 1, and we get 3 times 2 to the n minus 1 plus 1, which is 3 times 2 to the n minus 3. And then we have the other part of our formula here. So going from this step to this step, all we did was use the inductive hypothesis to replace f of n minus 1 with the formula we have. And now we can simplify. So we have 2 multiplying here. We have 2 to the n here. So we get 3 times 2 to the n plus 1. We also have this minus 3, which is multiplied by 2. So that gives us a minus 6. And don't forget this plus 3. And we get 3 times 2 to the n plus 1 minus 3. Minus 6 plus 3 is minus 3. Okay, let's check that. So we just proved that f of n equals 3 times 2 to the n plus 1 minus 3. And that is exactly the claim that we're trying to prove. So that's it. We are done. That's the end of the proof. Okay? So hopefully you've seen induction before. It's the kind of thing that is, when you first learn it, it's tricky to get your head around, but it's a really powerful thing, and it's the right thing to use in examples like this. Someone says, inductive what? Inductive hypothesis. Hypothesis is a thing that you think is true, and you're about to verify it. So we're thinking that it's true for all these smaller values, and we're going to verify that it's true for this bigger value, which establishes it for everything. How did I come up with the claim? I didn't come up with the claim, because this is from the textbook. We won't study in detail, but there are sort of general techniques for solving these kinds of things, for making these guesses. One of them is a really easy technique. You go to wolframalpha.com and you enter this equation, and it tells you the solution. Of course, you can't trust Wolfram Alpha to give you a correct answer, but in this case, I think it will tell you, it'll give you some closed form like this. And if you don't trust Wolfram Alpha, then once you know the claim, well, then the proof is not that difficult. Right? The proofs always kind of follow the same line. Check the base cases, check that it's true for the base cases, and then for the general case, apply the definition. That gives you something like f of n minus 1 or f of something smaller than k. Apply the inductive hypothesis, fight with the algebra, and then make sure that that looks like your claim. So, the proofs, once you have the guess here, are not difficult. In this case, I'm going to actually guess that the author of the textbook just cooked up this function in a way that he knew from the way he built it what the answer would be. It's easier if you get to make the function. You can figure out what the answer is going to be. When you took 1805, you assumed k. It was true for all. I'm assuming the question means for all k less than or equal to n, and then proved for n plus 1. Is there a difference? No, there's absolutely no difference. If you assume that it's true for all k from 0 up to n, then the next step is to prove that it's true for n plus 1. I don't like to do that, because, especially for these kinds of things, because I have a definition here that tells me the value of f of n. From that, I can guess the value of f of n plus 1, but, or not guess it, but I can figure it out. But the thing is, then I'm not just directly copying this line into this equation here. I would have to be copying, you know, f of, yeah, this thing here is just a copy of this, whereas if I had an f of n plus 1, well then there'd be an f of n here. Okay? So there's no difference. This is the way I like to do it. Okay, so a couple of examples beyond this. I'll write them down, and as I'm writing them, you guys submit your guesses as to what these functions really are. If there's other names for them. So here's one. F of n is equal to 1 or n times f of n minus 1. And it's 1 if n equals 0, and it is this if n is bigger than or equal to 1. Okay, there's one function. Maybe you guys can tell me what function that is. It's one you've seen before. And here's another one. Make sure I don't get it wrong. Okay, so let's see if there's any guesses as to what this function is. Yeah, this is factorial, right? If I expand this, I'll see that if I expand f of n, well, I get n times f of n minus 1. When I expand f of n minus 1, the first thing that I get is a n minus 1 times f of n minus 2. When I expand that, the first thing I get is a n minus 2 times f of n minus 3. So this thing expands into n times n minus 1 times n minus 2, all the way down to, the base case might look a little bit weird for you. It finishes with, here is the case when n equals 1, and then there's the extra case when n equals 0. But of course, multiplying by 1 doesn't change anything. This is definitely n factorial. And somebody correctly noticed that this thing here is Pascal's identity. And what was Pascal's identity about? Pascal's identity was for binomial coefficients, right? Pascal's identity says that n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. So if this is n choose k, then there's the n minus 1 choose k minus 1, and here's the n minus 1 choose k. And then there's the the boundary cases, n choose 0 is 1. So there's only one subset of size 0 of a set of size n. It's the empty set. And n choose n is also 1. How many subsets of size n are there of an n element set? There's only one of them. It's the whole set itself. So there's the 1. And then every other case, everything in between, is covered by Pascal's identity. All right. So b of n k is this, and in this case f of n is n factorial. So b of n k is just n choose k, and this is just n factorial. Okay, good. So now we're going to see something very cool. Some of you have seen it before because one of you at least guessed that it was the answer to one of these two questions. It wasn't. But what's cool about it is the closed form. So this is the Fibonacci function. So it's a function, f of n. It's recursive, and it actually has two base cases. It can be 0, it can be 1, or it can be f of n minus 1 plus f of n minus 2. It's 0 if n equals 0. It's 1 if n equals 1. And it is given by this formula if n is bigger than or equal to 2. And maybe you see why we need to have two base cases here. We need two base cases because the general formula refers not only to n minus 1, but also to n minus 2. So if I did not have this base case for n equals 1, then I would try and get f of 2, and I would see that that's f of 1 plus f of 0. And without this thing being defined, this would be undefined, right? The only thing that it just would not be defined. Okay? And if I tried to apply this formula, even though it says specifically that it's only for n bigger than or equal to 2, if I tried to apply that formula, which is incorrect, I would get f of 0 plus f of minus 1. And I really don't know what f of minus 1 would be. So there's two base cases here, and they're necessary because it needs to know the value of this function. The value of the function is defined in terms of two smaller values, that n minus 1 and n minus 2. All right. So let's do that little table. We have n, and we have f of n, 0, 1, 2, 3, 4, 5, 6, 7, 8. So when n equals 0, f of n is 0. When n equals 1, f of n equals 1. But when n equals 2, it's f of 1 plus f of 0. So it's also 1. When n equals 3, it's f of 2 plus f of 1. So that's 2. When n equals 4, it's f of 3 plus f of 2. That's 3. When n equals 5, it's f of 4 plus f of 2. So it's actually 5. Here it's going to be 5 plus 3 is 8. F of 7 is going to be 8 plus 5, 13. F of 8 is 13 plus 8, 21. We can go up to one more. 9, f of 9 is going to be 21 plus 13. That is 34. okay? And so on. So that's the Fibonacci function. Invented a long time ago by, probably not by this person named Fibonacci. Things are never named after the people who originally invented them. Let's say popularized by Fibonacci, who had a funny story about it, which is probably what made it popular. It has to do with the number of rabbits that you have after n generations of rabbits mating with each other. Somehow this thing here was supposed to be a model of at generation n in the mating of a bunch of rabbits, how many rabbits you have. Okay. So here is the very cool thing. So the claim is that the nth Fibonacci number is equal to phi to the n minus psi to the n divided by square root of 5. Where, well, there's two new variables here, where phi is equal to 1 plus the square root of 5 over 2. Psi is equal to 1 minus the square root of 5 over 2. And I'll write a note here because it'll be useful to us later. Phi and psi are the solutions to this equation x plus 1. Okay? So here is the thing that I think is absolutely incredible. It says that, well, look at this Fibonacci sequence. It's got this easy definition. It starts with two integers, 0 and 1, and everything else you just get by adding up the previous two values. So certainly all the values of the Fibonacci function are integers. Okay. Now, there's this insane claim here that says, actually, here's how I get the value of the nth Fibonacci number if I don't want to use the recursive definition. I take some number and raise it to the power n. I subtract some other number raised to the power n, and I divide by the square root of 5. So this is where things should look iffy to you. Square root of 5, that's not, it's bigger than 2, and it's smaller than 3. In fact, it's not even a rational number. So if you wrote down its decimal expansion, it goes off infinitely long. Okay, so we have this thing that we know is an integer, but somehow its formula involves dividing by square root of 5, an irrational number. And inside of there, up here, there's these two things. There's a 1 plus root 5 over 2 is this magic constant, and this 1 minus root 5 over 2 is this ugly magic constant. This one here is called the golden ratio. You may have heard of it. This one here is called the ugly little brother. Everybody loves the golden ratio. Everyone hates its ugly little brother. Okay, so now this looks like magic, and how you come up with this claim, actually there's a whole mechanism for doing that. But for now I'll say put this into Wolfram alpha. Wolfram alpha will give you the formula, and then all you have to do is a proof by induction that that formula is correct. I'm really going to do psi like that? Why wouldn't I do psi like that? What's wrong with psi like that? So let's prove this claim by induction. Okay. Proof by induction on n. So we have a couple of base cases. We have the base case n equals 0 that we need to do, and we're going to do it the same way we did before. We'll write down this formula, but we'll put 0 instead of n. So we get phi to the 0 minus psi to the 0 divided by square root of 5. Well, anything to the power 0 is just 1. So we get 1 minus 1 divided by the square root of 5, which is equal to 0. And 0 is indeed the value of f of 0. We have a second base case we need to deal with, which is this case, the base case n equals 1. So let's check that. So this says we should be looking at phi to the 1 minus psi to the 1 divided by square root of 5. Well, this one is a bit more work. So we actually have to look at the definition of phi and psi. So we get 1 plus square root of 5 over 2 minus 1 minus square root of 5 over 2, all divided by square root of 5. So let's see what cancels here. We have 1/2 minus 1/2. So those things go away. And we have root 5 over 2. There's two negatives here, plus another root 5 over 2. So that just gives me root 5. And on the bottom we still have the root 5, which is 1. And indeed, by definition, that is the value of f of 1. Okay. All right. And now, inductive step. We will assume f of k is equal to phi to the k minus psi to the k over square root of 5 for all k in 0 up to n minus 1. And then we're going to study f of n. And I hope I have enough room to get this done on this board. F of n, for n bigger than or equal to 2, because we've done n equals 0 and n equals 1. So we get to apply this definition. F of n minus 1 plus f of n minus 2. Right here that we're just using the definition. Following our procedure, well, we use the definition and now we have two versions of f on which we can apply the inductive hypothesis. Why can we apply the inductive hypothesis? Because the arguments here are n minus 1 and n minus 2, that means they're in this set 0 up to n minus 1. And the inductive hypothesis assumes that this formula is true for any k in that set. So let's do those. So this is going to be to n minus 1, we're going to get phi to the n minus 1 minus psi to the n minus 1 over square root of 5. Here we're going to get phi to the n minus 2 minus psi to the n minus 2 over the square root of 5. Okay, good. Let's clean this up a little bit. So everything is over square root of 5. Let's leave that alone for now. And we have some negative psi's and some positive phi's. So let's group them with each other. So phi to the n minus 1 plus phi to the n minus 2 minus, and I'll write it this way, psi to the n minus 1 plus psi to the n minus 2. Okay. So same formula, written slightly differently. All right. Let's do a bit of factoring here. So on this, for these two terms, they have a common factor, which is phi to the n minus 2. In fact, I can factor out that phi to the n minus 2. Now, to get phi to the n minus 1, I need to multiply that by phi. But to get this other one, I just need to multiply it by 1. And I'll do the same thing to these. So this is psi to the n minus 2 times psi plus 1. And still, everything is over square root of 5. Okay. And now, here comes the magic. All right. I have phi to the n minus 2 times this thing. I have psi to the n minus 2 times this thing. What I really want is phi to the n and psi to the n. So the only way that that's going to work is if this thing here is equal to phi squared, and this thing here is equal to psi squared. Now, I pointed out while I wrote this formula, or wrote this claim, that actually phi and psi are the two solutions to the quadratic equation x squared equals x plus 1. So here's x plus 1, which is equal to x squared. Right? For this value phi, x plus 1, that's this thing, is equal to x squared. So this really is equal to phi squared. This really is equal to psi squared, because these two things solve that. I mean, you can check that if you want, and if you don't, so once you see the solutions, you can check that they satisfy this, and if you didn't even know the solutions, you could use the quadratic formula to get those two numbers. But that's it. Now we're done. This thing here is phi squared. This thing here is psi squared. So that means this is phi to the n minus psi to the n divided by square root of 5. And that is exactly what we wanted to prove. So So this is incredible theorem is true. And to me, what's incredible about it is that there's these irrational numbers everywhere. They give you this formula, and whenever you evaluate this formula for a positive or a non-negative integer n, you get an integer which happens to be this solution to this equation. Now, it's not exactly magic. In fact, there's a mechanical way of doing this, which is why programs like Wolfram Alpha let you put in recurrence equations like this, and they'll give you these magic-looking solutions that you can then verify. But I mean, it is very cool. So because these Fibonacci numbers come up so much, it's worth maybe understanding a little bit about this thing. So I think the main thing to point out is that the actual values, like the numeric values of phi and psi, phi is approximately, I mean, it's irrational, so we can't write down the whole decimal expansion, but it's approximately 1.618. That's the beautiful golden ratio. Psi is approximately minus, well, 0.618304. Okay, so that's the ugly ratio. But the point about this is that phi, or psi to the n, it's heading to 0, right? If I take a number whose absolute value is smaller than 1, and I, let's say, square it, well, its absolute value gets smaller. And if I take it all the way up to the power of n, its absolute value is just getting closer and closer to 0. Okay? So as n gets big, psi is just heading off to 0. So that means that the Fibonacci number f of n is basically, you know, as n gets big, so as n gets large, this contribution of subtracting psi to the n, this is subtracting a number that's smaller than 1. And in fact, it's very close to 0. So it's almost exactly phi to the n over square root of 5. Okay? And if you don't like this sort of hand waviness, the difference between this thing and the real nth Fibonacci number is it's definitely smaller than 1. Okay? So if you want, you know, a quick and easy hack to get close to a correct answer for the Fibonacci numbers, just take this thing and raise it to the power n. You'll get, and divide by square root of 5. You'll get something that's very close to the correct thing. In fact, it's within 1. And for us, that means basically that these Fibonacci numbers, they're growing exponentially, and the base is this number, 1.61 whatever, unlike maybe some exponents that we're used to, like, you know, this is growing much more slowly than 2 to the n, but it is still growing exponentially. All right. So let's look now at a recursively defined set. Or, so let's say, These things are called 00 free bit strings. And I'm going to say let Sn be the set of n bit binary strings that do not contain two consecutive zeros. Okay, so for example, S of 0, that's the, it's not the empty set, I should be careful. It is the set that contains one element, which is the binary string of length 0. There's only one of them. It's hard to see it because it has length 0. So for strings of length 0, we usually use this notation epsilon to denote a string of length 0, because otherwise you can't see it, right? So that's one thing. What's S of 1? So these are binary strings of length 1 that don't have two zeros in a row. Well, there's one element of S of 1, and there's the other element of S of 1. There's only two binary strings of length 1. One of them is 0, it doesn't have two zeros in a row, and the other one is 1. S of 2 is where things finally become non-trivial. You get 0, 1, 1, 0, and 1, 1. And conspicuously absent here is 0, 0, because the string 0, 0 has two consecutive zeros. And S of 3 has 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and I'm missing one, which is 0, 1, 1. 0, 1, 1. Okay? So things that are not in that set, so, right, in S2, we don't have 0, 0. In S3, we don't have 0, 0. We don't have 001, and we don't have 100. Okay? So because all of these strings have two zeros in a row in them. So that's the set that we're going to study. Thank you for the answers. Unfortunately, with the latency, they only come in 10 or 15 seconds after I've actually asked the question. But thanks, it's nice that you're paying attention. So what we'd like to know is, how big is S of n? So in particular, let's define now let's just leave it like that. Okay, so we'd like to know how big S of n is, and I know the answer for a few values of n. When n equals 0, the size of S of n is equal to 1. When n is equal to 1, the size of S of n is equal to 2. When n is equal to 2, the size of S of n is equal to 3. And when n is equal to 3, the size of S of n is equal to 5. So there's some values that I know, and I could try and do S of 4 here. But we'd like to get this for the general case. So and the idea is that we can do this by getting a recurrence or a a recursive equation that will tell us the size of S of n. So let's look at a string that's in S of n. So here's what a string in S of n can look like. It starts with a 1. So, and then there's n minus 1 other things, other positions in this string. And as long as I write, whatever I write here doesn't have 2 consecutive zeros, then the whole string of length n will not have 2 consecutive zeros. So in here, that means I can put any string of length n minus 1 that does not have 2 consecutive zeros. So that means here can be any element of Sn minus 1. That's the definition of Sn minus 1. It's a bit string of length n minus 1 that doesn't have 2 consecutive zeros. So a string in Sn starts with a 1 followed by any string in Sn minus 1, or, and this is exclusive, now it's tempting to say starts with a 0 followed by something, but the problem with that is if I say the string starts with a 0 and it's followed by some string of length n minus 1, then just because the string of length n minus 1 doesn't have 2 consecutive zeros in it, doesn't mean that I get a string without 2 consecutive zeros. In particular, here's a string that I can put here. That's a string that's in S of n minus 1, right? It's of length n minus 1, it doesn't have 2 consecutive zeros. But if I put it here, now I actually end up with a string that has 2 consecutive zeros. So I have to be a little, just slightly more clever and say, well, if it starts with a 0, it cannot start, the next thing cannot be a 0. So actually the next thing has to be a 1. So if my string starts with a 0, it actually starts with a 0, 1. At least for n bigger than or equal to 2. So it starts with a 0, 1. And then there's n minus 2 things, more bits in the string. But now the nice thing is, if I write down any string here that doesn't have 2 consecutive zeros, then I get a string of length n that doesn't have 2 consecutive zeros. So that means what can go here is any element of Sn minus 2. So it starts with a 0, 1 followed by any string in Sn minus 2. Okay? Good. So let's recap a little bit. So a string in Sn either starts with a 1 or it starts with a 0, 1. Those are two mutually exclusive things. So imagine Sn is a set, and I've partitioned it into 2 subsets. The strings in Sn that start with a 1 and the strings in Sn that start with a 0, 1. Okay? So if this is what I'll call A and this is what I call B, then Sn is equal to A union B, and A and B are disjoint. Okay? So that means the size of Sn, we can use the sum rule because A and B are disjoint, is equal to the size of A plus the size of B. We don't have to worry about inclusion-exclusion exactly because A and B are disjoint. All the strings in A start with 1, all the strings in B start with 0. So there's definitely no string that is both in A and B. Now, how big is A? Well, A starts with a 1. Everything in A starts with a 1, so there's really no choice there. There's only one way to do that. And then you pick anything from Sn minus 1. So that means that the size of A is actually the size of Sn minus 1. Right? Take anything from Sn minus 1. There's this many ways to choose a thing from Sn minus 1. And then you write a 1 in front of it. There's only one way to do that. Similarly with B, well, to get a string in B, you pick any element from Sn minus 2, and then you put a 0, 1 in front of it. So that means the size of B is the size of Sn minus 2. Okay, so that means the size of Sn is equal to the size of Sn minus 1. Well, let's be more careful. It's equal to 1 if n equals 0. It's equal to 2 if n equals 1. And otherwise, it's equal to the size of Sn minus 1 plus the size of Sn minus 2. And that's true if n is bigger than or equal to 2. Okay? Now, maybe that looks familiar to you. If not, well, we can maybe go back and write down the Fibonacci sequence that we had. Fibonacci started 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. So this was Fibonacci. And our sequence here, Sn, so we'll write down Sn. So it has it starts with a 1, then it has a 2, and then it has this formula, which is just like the Fibonacci formula. So our sequence that we're studying right now starts with a 1, starts with a 2, and then it's the Fibonacci formula. So this sequence that tells us the number of 0, free bit strings of length n is very closely related to the Fibonacci sequence. In fact, it just seems to be offset. Instead of starting at 0, like the Fibonacci sequence does, it starts at the second 1 in the Fibonacci sequence. And so really what that means is that S of n is equal to, I'll say Fibonacci because we've been calling everything f, Fibonacci of n plus 2. All right, so a strange looking question about strings that avoid 2 zeros in a row. and weirdly the Fibonacci numbers come up. All right, so let's change this a little bit. And let's do, instead of counting binary strings, let's count strings over a 3-letter alphabet, and I'll say call them AA free strings. Okay, over another little alphabet, 3-letter alphabet A, B, and C. So I write strings of length n over the alphabet A, B, C, so all the characters are A, B, or C. And I don't want 2 consecutive A's. So very similar question, right? You can think of A as a 0, B as a 1, and C as a 2, but we just studied the case where there was only A and B, strings over A and B, and we didn't want 2 consecutive A's. We got the answer. So what happens when you just add an extra letter here? So the question is, how big is Sn? Oops. I don't want to, well, I guess I can do a small example. S of 0 is just the empty string. S of 1 is AB, has 3 strings in it. These are the 3 strings of length 1. S of 2 has lots of strings in it. It has AB, it has AC, it has C, let's say, BA, BB, BC, CA, CB, CC. Okay. Right. The number of strings of length 2 over a 3-letter alphabet is 3 squared, is 9. But in this particular set, one of those 9 strings is missing. The missing string is the AA. And I don't want to do S3 because it gets big, right? So there's already 27 3-letter strings, and then I have to make sure I don't hit any of the ones that have two A's in them, so I won't do that one explicitly. But maybe we can follow this routine and see if we can get a nice recurrence here and maybe solve that. So still using this Sn, a string in Sn, so this is an n-letter string whose letters are made up of A, B, and C. So it could start with B, followed by, so if I put a B here, then what can I do with the remaining n-1 positions? Well, I can put anything I want there as long as it doesn't have 2 A's in a row. Okay. Good. So that's one of these things. So it could start with a B. It could also start with a C. And followed by anything in Sn-1. Right, this picture doesn't change. If I, instead of putting a B here, if I put a C here, then I can put anything here as long as it doesn't have 2 A's in a row. So there's option 1 is it starts with a B, option 2 is it starts with a C, and option 3 is it starts with AB. Option 4 is it starts with AC, and there's no option 5. It's not allowed to start with AA because we're trying to avoid 2 A's in a row. Okay, so let's look at the AB case. The AC case will be the same. So if I put in AB here, I have n minus 2 other locations to fill in. I can put any string there as long as it doesn't contain 2 A's in a row. So indeed, it's any element of Sn minus 2. Followed by anything in Sn minus 2. And similarly, if I put an AC here, that doesn't change anything. I can put anything from there afterwards. Anything from Sn minus 2. Okay. So what does that give us? Well, that says that using exactly the same reasoning, these define 4 different kinds of strings. These ones start with B, these ones start with C, these ones start with AB, these ones start with AC. So we're going to have, in this case, the size of Sn. We'll have 2 base cases. We get 1 if n equals 0. We get 3 if n equals 1. And otherwise, we get, well, we could get, what's the size of this thing? It's the size of Sn minus 1. Right? Take any string from Sn minus 1 and put a C in front of, or a B in front of it, you get something from here. But also you can take any string of Sn minus 1 and put a C in front of it and you get something from here. Or you can take any string from Sn minus 2, put an AB in front of it, or you can take anything from Sn minus 2 and put an AC in front of it. Of course, this simplifies a little bit, right? We have 2 Sn minus 1s, we have 2 Sn minus 2s, so let me just write that way. Okay. So there's the recurrence you get for the size of this set. So how many strings over the alphabet, A, B, C, where you don't have 2 A's in a row? How many strings of length n? Size of that set is given by this recurrence. And here's the claim. Okay, and I'll just point out that this thing, I don't know, let's call this alpha and let's call this one beta. These are solutions to okay. So turns out there is a closed form for this equation. It looks like this. There's a bunch of root 3's in it. You divide by 6 instead of root 5, which is nice. It looks kind of like what happens with Fibonacci numbers. There's a golden one raised to the power n, and then there's a ugly negative one raised to the power n. So that's good. And these two magic numbers here, they come, well, they come from the fact that they're the solutions to x squared equals 2x plus 2. Okay. So if we wanted to, we could prove this, just like we did for the Fibonacci numbers. I won't do it. If you're interested in an exercise, you can. And if you decide to go ahead and do that exercise, it follows basically the same lines as the Fibonacci proof, but at some point you do this factoring out, and what you get is this thing, 2x plus 2, and you want to replace it with x squared. So that's exactly the same thing is going to happen if you do this. Okay, so that's a sort of easy, well, not an easy thing, but once we did the 0, free bit strings, the AA free strings over ABC, they don't seem so bad. So let's do one more example and see what happens. So now I'm interested in not AA free strings, but AB free strings. Okay. So same thing, except instead of saying they don't contain two consecutive A's, they do not contain AB as a, I'll be specific, consecutive substring. So in this case, S of 0 is the same, it's the empty string. S of 1 is the same because nothing happens. But S of 2 is different. Instead, it's not allowed to have AB in it, but it is allowed to have AA. So it has the same size, it's just a different set of strings. So it should not have AB in it. We'll get rid of this claim because it referred to the previous question. So after this, you might think, okay, the answer is going to be the same. I mean, so what? In the first example, I ruled out a particular string. It happened to be two A's. In this example, I won't let you use this other particular string. It's an A and a B. And we did the first few, and look, we got the same answer. Yeah, the set was different, but the number of strings was the same. One of them is missing. So you might think, okay, the answer is going to be the same. But you know, you should still continue with this and see where it leads you. And that means you should try and keep making this argument. So, so a string in Sn, it could start with a B, and then I put anything that I want here, and I will not get anything I want that doesn't have an AB in it, and when I tack a B on the front of that, I won't get an AB showing up in my string. Okay. Similarly, if I put a C here, take anything that I want, n of length n minus 1, that doesn't have an AB in it, and when I attach a C to the front of that thing, I still won't get an AB. So these two things check out. Now, this one certainly has to change because I'm not allowed to start with an AB, but I could say it starts with an AC, So if my string starts with an A, C, then put anything that I want here of length n minus 2, as long as it does not have an AB in it, when I attach AC to the front of it, I won't get an AB in the entire string. Okay. Well, so this is followed by anything in Sn minus 2. This is really looking like the same answer. So what's missing? We said you could start with a B, you can start with a C, you can start with an AC. You're not allowed to start with an AB. But there's still one thing missing from this list. Maybe it starts with an AA. Okay, let's see if that works. Here, you start with an AA, then you have n minus 2 slots. Oh, I can't just put anything in here. In particular, I can't put this string there. That's a string from Sn minus 2. It does not have an AB in it, and it has length n minus 2. But when I tack a AA onto the front, then I have a problem because I get I have an AB there. Okay. Darn. So what can I put here? Well, I'm not allowed to put a B here, so maybe I could put a C here. But then things get weird, right? So instead of saying you start with AA, you start with AAC, followed by anything in Sn minus 3. Right? This is minus 3 now because there's 3 characters on the front. And that still doesn't finish everything. So I still need to make sure I've covered all the bases, but my string could still start with A, A, A. So there's another thing that I need to consider, which is what if it starts with A, A, A? Well, then what's the next letter? It could be a C, or it could be another A, and a C, or it could be another A, and a C, and so on. So actually, this list will go on, and it'll have something like n steps in it. And if you do this, you'll find that you get a recurrence like the size of Sn is equal to 2 times the size of Sn minus 1. That's from these first 2 steps that checked out, plus the sum, and I think you run from k is equal to 0 to n minus 2 of the size of Sn minus sk. So, this is just an illustration to show you that even when you change the problem just a little bit, the answer can change drastically. So it seemed kind of innocuous, saying instead of looking out for AAs, just saying, oh, let's not have ABs. And indeed, it started out being exactly the same, and then we realized at some point that actually it's not. Things get wildly different. We don't have here a formula that has just an Sn minus 1 and an Sn minus 2 in it. It has an Sn minus 1, Sn minus 2, Sn minus 3, Sn minus 4, all the way down to S0. So this one is harder to solve. I don't know if Wolfram Alpha will do this one for you. But there you go. Just to let you know that these things can get out of hand quickly, and intuition is not a good guide here. You need to check everything that you do. All right, so that's a good place to stop for today. Would anyone like to ask me some questions? Why can't it start with a BC? Well, if it starts with a BC, then it starts with a B. We've already counted the things that start with B. Okay. This accounts for strings that start with A and BA. Strings that start with BA start with B, so they're counted here. Strings that start with BA, yeah. Yes. So in one of the examples, in fact the first example, I had f of n is equal to 2 f of n minus 1 plus 3. And in the inductive step on fn minus 1, I used 3 times 2 to the n. I'm assuming you used FOIL on the next step, but I can't figure out how you ended up with 3 times 2 to the n plus 1 minus 6. Yeah, okay. So, yeah, okay. So, just very quickly, so see if it's still in my head. So we had 2 f of n minus 1 plus 3. That was from the definition. Here we used the inductive hypothesis. We got inductive hypothesis says 3 times, no, inductive hypothesis says 3 times 2 to the n, and there was a plus minus 3, and then we have this plus 3. Right, that's what we had. So 2 times 3 times 2 to the n, that's equal to 3 times 2 to the n plus 1, right? So that's one of the terms. 2 times minus 3 is minus 6. And then we still have this plus 3 here. Okay? So the thing that you're saying 2 times 3 is 6, well, the 2, I mean, it's 3 times the extra 2 is in the exponent now. Yes, class is over. I'm just answering questions now. Okay. All right. So thanks for tuning in, and I'll see you next week.